Is lecture number 8, and we start new chapter, that is forces on immersed bodies. Now, before we start this chapter, we should first see that why we need to study this chapter. Clear? So you can see here in this picture, the wake of a Boeing 767 disrupts the top of a cumulus cloud and clearly shows the counter-rotating trailing vortices. So in this case, you can see that now when this aeroplane, it moves through the air, so you can see the behavior. Clear? And now in fluid mechanics, when a body is moving through a fluid, for example, now here aeroplane moving through the air, and we have clouds there, or if a fluid is moving past an object, so this is treated similar. Clear? So now in this case, you can see here that counter rotating means that you see this rotates in this direction here, and this rotates in this direction here. Clear? So these are the trailing vortices, and this is similar phenomena we are going to observe when we study the forces which are acting on bodies when they are moving through the fluid. Clear? So learning objectives for this chapter: after completing this chapter, you should be able to understand the causes of drag and lift. These are the forces which are acting on a body when a body is moving through a fluid. We will study in detail what are the different forces acting, how to calculate them, and the causes of these forces. Clear? We will calculate these two types of forces which are acting on a bodies for different types of objects. Clear? We will also explain fundamental characteristics of boundary layer. We already studied about boundary layer formation in pipes. Similarly, when a body is moving through a fluid, so again a boundary layer develops on the surface of a body, and we will study different characteristics of the boundary layer, including laminar, transitional, and turbulent regimes. Similarly, we will learn how to calculate the boundary layer parameters. For example, the shear stress, the thickness of the boundary layer for flow past a flat plate. And you should be able to provide a description of boundary layer separation after we complete this chapter. So we will study what is boundary layer separation, why it occurs, and what are the effects when we have boundary layer separation. Clear? So after finishing this chapter, you should be able to answer all these questions. Now, before we start this chapter, so we should know the difference between internal and external flow. So a fluid flow is classified as being internal or external depending on whether the fluid flows is confined space or over a surface. Clear? So when it is confined space, then we can say it is internal flow, or when the fluid flow is over a surface, then we can say it is external flow. To further clarify the concept, the flow of an unbounded fluid over a surface such as plate or a wire is external flow. Example, air flow over a ball. For example, in this case, you can see that we have flow over a tennis ball, and you can see the streamlines, how the flow passes tennis ball. Clear? So this type of fluid flow is known as external flow. You can see here the body is surrounded by a fluid. Next, the flow in a pipe or duct is internal flow if the fluid is completely bounded by solid surfaces. Example, water flow in a pipe. So as we already studied the previous chapter, so the flow always occur in a pipe. Now in this case you can see that the fluid is completely surrounded by a solid surface. So this is known as internal flow. Clear? For example, here you can see this pipe flow, this is internal flow. So we already studied about the internal flow in which the fluid is surrounded by a solid surface. For example, a pipe shown here as an example. But in external flow, what is happening that the body is surrounded by a fluid, clear? Unbounded fluid over a surface. So this type of flow is known as external flow. So this chapter we will study about external flows in which the body will be surrounded by fluids. Now introduction. Fluid flow over solid bodies frequently occurs in practice, and it is responsible for numerous physical phenomena such as the drag force. We will study in detail what is a drag force, that is acting on automobiles, power lines, trees, and underwater pipelines. The lift developed by aeroplane wings, these are forces, clear? Upward draft of rain, snow, hail, and dust particles in high winds. The transportation of red blood cells by blood flow. The entertainment and disbursement of liquid droplets by sprays. The vibration and noise generated by bodies moving in a fluid, and the power generated by wind turbines. So you can see here that different practical applications that we encounter in our daily life, fluid flow over solid bodies will occur in all these examples. Clear? So that's why you can see here that external flows where the body is surrounded by a fluid, clear? So it has numerous applications. That's why we need to study this chapter, clear? So a fluid moving over a stationary body, such as the wind blowing over a building, and a body moving through a quiescent fluid, such as a car moving through air, are referred to as flow over bodies or external flow. So you can see here that wind blowing over a building. So because you see that we are civil engineers, so we want to calculate the loads acting on the buildings that we design. One of the load is the wind load. So that's why we would be interested to know how to calculate the wind load, clear? Similarly, a body moving through a quiescent fluid, quiet fluid, such as car moving through the air, this is very common application around us. So we would like to know that what forces are acting on a car, clear? And then how we can calculate them, clear? Because calculation of these forces will play important role in the design of these vehicles, clear? So these all are examples of external flows. Clear? Now again, applications. You can see here that flow over bodies is commonly encountered in practice. For objects moving through a fluid, such as automobile, bird, determine the power requirements. Clear? You can see here that aeroplane is moving through the air. So we would like to know how much power is required to move this aeroplane through the air. Clear? For structures, for example, bridge, signboards, towers, determine the wind loads. So as I said that these structures are very common around us, and we would like to calculate the wind loads acting on them so that we can design these structures and they are stable to withstand these loads. Clear? For falling objects, for example, pollen spore, parachute, calculate the terminal velocity. So whenever we use parachute, when the paratrooper they jump from aeroplane, so we would like to calculate what is the terminal velocity. I will explain that what is the terminal velocity, because you already know from previous classes that whenever a body is falling through the air, clear, so first it accelerates, and then after some time the equilibrium between the forces occur, and then the acceleration becomes zero, and the body is moving with a constant velocity. So that constant velocity, that is known as the free fall or terminal velocity. So in applications such as parachute, etc., we would like to know that what is the terminal velocity. And this is not only for the air but for the water also. If we drop an object, for example a sphere, and it moves through a water, so we are interested to calculate what is the terminal velocity. Clear? For a wing of aeroplane, determine the lift force. So as you can see here, that because of the lift force, the aeroplanes they are able to fly in the air. So we would like to know that how much lift force is required for that purpose. So you can see here the importance of studying this chapter. We have numerous applications in civil engineering as well as in other branches of engineering that involves external flows. Clear? Now, flow classification. The velocity of the fluid approaching a body is called the free stream velocity and is denoted by v. So the velocity with which the fluid will approach the body, that is known as the free stream velocity. We will denote it by v because in the previous chapter we use all the time this v to denote the velocity. If you study the textbook or in other books, so they are using other notations, clear, for this, such as for example they are using the notation u, or in some books maybe you find the notation they use u infinity. This is just the free stream velocity, the notation that they use to denote. Clear? The reason for this is that you can see here when we have this velocity, when we have a two-dimensional flow field, so then in that case the flow can occur in x direction and also it can occur in y direction. Clear? So that's why if you remember when we study the turbulence, clear, in that case we denoted that the velocity vectors are u in the x direction. Clear? So that's why in that context the different books they use this as denoted by capital U or u with infinity. Clear? So this is the reason, but it will create a confusion because for example you denote the velocity with v and then in another chapter we denote the velocity with u. So that's why for this purpose in this course we will try to denote this velocity by v, just to be consistent with previous chapters. But remember, in the textbook as well as in other books, you will find the notation u or u infinity. This is just a notation used to denote the free stream velocity. Clear? So because they use it that, okay, we can have a two-dimensional, three-dimensional flow fields. Clear? So that's why the free stream velocity should be denoted by u, indicating that it is only in the x direction. And once it passes through the body, then it can have two components. Clear? You can see here that this velocity fluid, when it moves with a velocity v, here as shown here, it is a two-dimensional flow field. Clear? But anyhow, just to be consistent with the previous work, I prefer to still denote it by v. So please remember this. Now, flow classification, we can have two-dimensional. What does it mean? Infinitely long and of constant cross-section size and shape. So you can see here that when this fluid passes a body, then it is a two-dimension because it can have x and y components. The second one is x is symmetric. What we mean by x is symmetric? Formed by rotating their cross-sectional shape about the axis of symmetry. You can see here, if we rotate this body about this x-axis, so there is a symmetry. Clear? So that's why it is known as axisymmetric. And the third one is three-dimensional. So in three-dimensional may or may not possess a line of symmetry. There is no symmetry. Clear? When this fluid passes the aeroplane, it can move in the three directions. So that's why this type of flow is classified as three-dimensional flow. Again, you can see here that this type of flow, this is an example of 2D. For example, a bullet moving through the air, this is an example of axisymmetric. Clear? And a car, essentially the flow of the fluid passing through this car, so that will be three-dimensional flow. So this is the different classification of flows that we can encounter while dealing with external flow problems. Now, in external flow, the shape of the body affects the flow characteristics. As you can see here, that when the shape of the body is different, so it can affect the flow characteristics. Bodies subjected to fluid flow are classified as being streamlined or bluff, depending on their overall shape. So this is now regarding the shape of the bodies. We can classify them as being streamlined or bluff, and that will depend on their overall shape. So a body is said to be streamlined if a conscious effort is made to align its shape with the anticipated streamlines in the flow. Streamlined bodies, for example, airfoils, racing cars, etc., have little effect on the surrounding fluid. So such type of bodies such as airfoils. I will explain later on what we mean by airfoil. It is just like the shape of an aeroplane wing. And we have racing cars, you might have observed their shape. These are known as streamlined. Clear? And we will study that what is the purpose of streamlining. After we study that what are the different forces which are acting on a body when it is moving through a fluid, so then we will know that what we mean by streamlined bodies. Clear? And what is the advantage of that? A body such as a building, a parachute, etc., tends to block the flow and is said to be blunt or bluff. So such a bodies which block the flow, clear, they are said to be bluff or blunt bodies. For example, a building or a parachute. Clear? Now in this example you can see here that two cars are shown here. Now in the above example you can see the shape of the car. So in order to move this car at the speed of 60 miles per hour, you need a power of 70 horsepower. But if we can streamline a body such as shown here, another car, then in this case you can see here, just to move this car with the same speed as 60 miles per hour, see the speed is the same, you only require 50 horsepower. So in this way you can see that the shape of the body plays important role. Clear? The shape of the body, it affects the flow characteristics. So you can see here that it is much easier to force a streamlined body than a blunt body through a fluid, because you can see here in this example that we streamline the car, so it requires less power to move it through the air. Now lift and drag concepts. In the previous slides we studied that what is external flows. We learned that internal flow is that when the fluid is surrounded by a body such as a pipe flow. We already studied that in detail in the previous chapter. And the second type is external flow, where the body is surrounded by a fluid. So in this chapter we are going to study this second type in detail. We studied about different practical applications that we encountered that highlights the importance of studying this chapter. And then we studied about the flow classifications, clear, and we studied about the different body shapes that can affect, clear. So now we study that what are the different forces which can act on the bodies. So as you can see here, just an example shown here that we commonly see is that high winds knock down trees, power lines, and even people as a result of the drag force. So commonly when air is blowing with high speed, so we commonly encounter these problems, clear, that high winds knock down trees, power lines, and even people as a result of the drag force. So now in this topic we are going to learn that what is a lift and drag force. So a body meets some resistance when it is forced to move through a fluid, especially a liquid. A fluid may exert forces and moments on a body in and about various directions, as you can see in this figure. So drag, the force a flowing fluid exerts on a body in the flow direction. So now this is the basic definition of a drag force, that it is the force a flowing fluid exerts on a body in the direction of flow. So whenever, remember, now that we will try to calculate different forces acting on bodies when they are moving through the fluid. So when a fluid is stationary and body is moving through the fluid, or when body is at rest and fluid is moving past the body. So this is the same problem. In fluid mechanics, this is treated as the same problem. Clear? When a fluid is stationary and body is in motion, or when a body is at rest and the fluid is in motion flowing past the body, so this is the same problem in fluid mechanics. So the force that will be exerted by the fluid on a body in the direction of flow, that is known as the drag force. I will further highlight this by visual examples. Clear? The drag force can be measured directly by simply attaching the body subjected to a fluid flow to a calibrated spring and measuring the displacement in the flow direction. So this is in experimental way. Clear? We can calculate the drag force. Clear? So how we can calculate it? That attaching the body subjected to a fluid flow to a calibrated spring and measuring the displacement, clear, in the direction of flow. So we can calculate that how much drag force is acting on the body. Now, drag is usually an undesirable effect like friction, and we do our best to minimize it. So in most of the cases, these drag forces which are acting on bodies moving through the fluids, so this is undesirable effect. Clear? Because the more is the drag, the lesser will be the speed. But for example, in the vehicles that we are using to travel from one point to another point, whether it is a car, a bus, a train, or aeroplane, so we want to reduce the drag force. Clear? So that it can move faster. So in most of the cases, it is undesirable. And we are always looking for how to reduce the drag forces on the moving bodies. Clear? But in some cases, the drag produces a very beneficial effect and we try to maximize it, for example, in automobile brakes. So when we apply the brakes in automobiles such as car, bus, etc., we want to stop it in a short interval. So then in that case, the drag force can be beneficial. Clear? Next, we come to the lift force. So lift is a force that acts on an immersed body normal or perpendicular to the relative motion between the fluid and the body. So what we studied about the drag force, that it is the force acting on a body in the direction of motion. Clear? That is in the direction of motion. Clear? Of the moving fluid. Lift is a force that acts on an immersed body normal or perpendicular to the relative motion between the fluid and the body. The most commonly observed example of lift is that of aeroplane wing supported in the air by this force. So the very common example of lift is that we see around us is that of the aeroplane wing supported by this force in the air. Clear? You can see here in the aeroplane these four forces are acting because the aeroplane, it moves through the air, so it has weight, and weight is acting down, acting through the center of gravity of the aeroplane. Similarly, when we fly the aeroplane, so we have this engine here, so this engine, it exerts a thrust. Clear? It moves the aeroplane in the forward direction, and because the aeroplane is moving through the air, so the air will exert a drag force on this aeroplane. Clear? So you can see here that this force in the direction of the motion of the fluid. Clear? This is what we defined here. The force a flowing fluid exerts on a body in the direction of flow. So that's why you can see here that this is in the direction of flow of the fluid past this aeroplane. So this is known as a drag force. And lift force, it acts on a Earth's body normal or perpendicular to the relative motion between the fluid and the body. So this is the lift force. Clear? And it acts on this aeroplane wing. Clear? This is the main purpose that the two wings are provided in aeroplane in order to generate this lift force. Because of the lift force, the aeroplane is able to fly in the air. Clear? So you can see here that the air, it flows in this direction. Clear? Air, it flows in this direction. So the force which is acting parallel to the direction of flow of fluid, that is the drag force. Clear? And the force which is acting on a body normal or perpendicular. Clear? So that is known as the lift force. So these are the two forces which are acting on bodies when they are moving through the fluid, and we are interested to calculate them. Clear? Similarly, you can see here when aeroplane flies through the air, so commonly these four forces are acting. The thrust, which is generated by the engine, aeroplane engine, so it moves the aeroplane in the forward direction because the aeroplane has its weight which will be acting downward, and because the aeroplane moves through the air, so because of that a drag force will be acting on this aeroplane. This drag force is basically a resisting force. Clear? And because of the motion of the aeroplane, so on the wings this lift force will be developed, and this helps the aeroplane to fly through the air. So you can see here the important concept of the drag and lift forces, and that's why we are interested to calculate them. Clear? Now, when we fly a kite through the air, so you can see here that the motion of the air is represented by this free stream. Clear? And when the kite flies through the air, so these two types of forces are acting. Clear? So the drag force is the component of the force parallel to the free stream. You can see here that this FD, it is parallel to the free stream. So this type of force is known as drag force. These are the basic definitions of these two forces. Later on we will learn how to calculate them for different bodies. And the lift force is that component of force perpendicular to the free stream. So you can see here that the lift force, which is denoted by F with a subscript L, so this is the force which is acting on a body perpendicular to the free stream. Clear? So these forces, they are acting on the kite due to air flowing over the kite. So remember, now these are the two principal forces which are acting on bodies when they are moving through the fluid. So now, as I said earlier, that when a body is stationary and the fluid is flowing past the body, or when the fluid is stationary and the body is moving through the fluid, remember this is treated as same problem. So in either case, these two principal forces will be developed. One is known as the drag force and the second one is known as the lift force. So the basic definitions are that the drag force, it will be the component of the force that will be parallel to the free stream. You can see here it is parallel to the free stream, and the force which is perpendicular to the free stream, that is known as the lift force. So now that we know that two principal forces are acting on bodies when they are moving through the fluid, now in this diagram you can see here that this is airfoil, clear. The aeroplane wing, if we see here, if you cut the aeroplane wing here and you would like to see the shape, if you take the cross section here, so the cross section can look like this, clear. So when a fluid is moving past this object, so these two forces are developed. One is in the direction of the free stream, so that is the drag force denoted by F with a subscript D, and another force which is acting perpendicular to the free stream, that is known as the lift force, clear. So now before we see how to calculate these two forces acting on any body, clear, you can see here this is the pressure distribution around this body as a result of motion of this body through the fluid, clear. So you can see here that this pressure distribution diagram, this I will explain later on in detail when we study the lift in detail later on in this course. So at the underside of this object here, a pressure greater than 0 is developed, but on the top surface of this object the pressure is negative, clear. And you can see here that at the bottom we have a greater pressure and at the top we have smaller pressure. So that's why what will happen, that because of this pressure variation, a force will be generated which will be acting upward, clear, from high pressure to low pressure, and this we call as the lift force. This is how the lift force is generated, clear. So this we will study in detail later on, that why a pressure greater than 0 develops on the bottom surface, and on the top surface why a pressure less than 0, or you can say negative pressure, develops. And because of this difference, so you can see high pressure below and low pressure above, this will create a net force, net upward force for this situation, and this we call it as the lift force, because perpendicular to the free stream. If the situation is that we have greater pressure, if for example on the top surface P is greater than 0 and at the bottom P is less than 0, if this is the situation, then what will happen, that a downward force will be created, clear. And then in this case this lift force will be in the downward direction. This force will be in the downward direction. So this we will study in detail, that why this is created, this situation is created, that we have a greater pressure at the bottom and negative pressure at the top. But this explains the mechanics, that how this force is created. And this drag force, this is due to the shear stresses which are generated. Clear? As you can see here that when this fluid moves past this object, clear? So what will happen? We already studied about that it will create the shear stress on the surface of the body. Clear? So forces from the surrounding fluid on a two-dimensional object, we have the pressure force, clear, and viscous force, and the resultant force lift and drag. Clear? So remember now that whenever a fluid flows past an object, so two forces will be acting. One will be the pressure force, and we already studied before, you might have studied about pressure in detail in fluid mechanics 1, that pressure force is that force which acts perpendicular to the area, normal to the area. Clear? And then the resulting stress is the normal stress. Clear? And also we have a shear force, clear, which acts parallel to the area, and that creates a shear stress. Clear? So because of these two forces acting, so this results into these lift and drag forces. So this, now we are moving towards the concept that how we will calculate these two types of forces. So now in this case, we consider a small portion, clear, of this body. For example, you consider any part here. Let's say I consider this small part of the body surface shown in this diagram, and this I highlight here. This is shown here. Clear? So as we learn that whenever the fluid is moving past the body, then these two forces will act. One will be the pressure force, clear, which will be acting perpendicular to the surface, and the second one will be the shear force. Clear? So stress, that is force per unit area. Clear? We defined that stress, that is equal to force by area. So the same concept is used here. It is equal to force by area. So now stress multiplied by area is your force. Clear? So that's why we show them here as the pressure and shear forces. Pressure and shear forces on small element of the surface of the body. So now that this is clear, so these forces, you can see here that if we want to resolve them into XY plane, clear, so they are shown here. The orientation is shown here that this PDA, it makes an angle theta with the horizontal, because you can see here, since this is the theta, so this line will make the same angle with two parallel horizontal lines. So that's why this theta and this theta, these two angles are the same, this angle and this angle, because these are alternate angles, as you have already learned in mathematics. So this theta that we show here, this is arbitrary. It is not that always this angle orientation will be made by these forces. No, this is just how you look to that. And then accordingly, we resolve them into components in order to calculate the resultant forces. Clear? So that's why this theta is not always the case like this. This is just shown in this diagram, and accordingly, we will try to develop expressions for the forces. And now we have this one pressure force which makes an angle theta, and another one is the shear force, which is then perpendicular to this normal force. So now we would like to do what? We would like to resolve them into components. Clear? Because earlier we stated that the drag force that will be acting in the direction parallel to the free stream. This is the free stream velocity. So now I'm interested to calculate that what is the force acting in this direction. And then I'm interested to calculate what is the force acting in perpendicular direction to this, means in x and y direction. So that's why I have to resolve these two forces into components so that I can calculate the forces in x and y direction. This is how we started with the definition of the two forces, the lift and the drag forces. Clear? So now what we do is that this PDA, it makes an angle theta with the horizontal, so it is easy. We can easily resolve this into components. For example, if I just try to draw it here, so you see this is the component here, PDA. This is P, the pressure, multiplied by dA is the force. And now it makes an angle of this here. Clear? It makes an angle of theta. So now it is easy to resolve this into components, because one will be this component here, one will be this component, and this will be equal to P into dA into cos of theta. Clear? This will be equal to cos of theta, and one will be this angle here, this component for PDA, and this will be equal to PDA into sine theta, into sine theta. Clear? Because the side opposite to the theta, that is the sine theta. And then next I have to resolve this force here, tau W. Tau W is what? This is the wall shear stress. Whenever a subscript W appears, so it means that it is the wall shear stress. So times dA, this is the shear force. Clear? So now how to resolve this into components? So you can see here, if I try to resolve this into components, so again you can consider the trigonometry here. You see that this is that force PDA, and then what happens is that this PDA is perpendicular to the shear stress. This is perpendicular here. If I can draw here, so you see that it is perpendicular to this shear stress, tau W, the wall shear stress, into dA. So what it means is that this angle is 90 degree. This angle is 90 degree between the two. This is what is shown here. Clear? So when this angle is 90 degree, and if I draw a horizontal line here, clear? I draw a horizontal line here and I extend this, clear? I extend this, simply this line here to join. So now this angle is shown as theta. This angle is theta. So now when this is theta and this is 90, then this angle must be 90 minus theta. Clear? This angle must be 90 minus theta. So when this is 90 minus theta, if I draw again a horizontal line here, so this angle and this angle will be the same. This angle will also be 90 minus theta, because these are alternate angles. Clear? This is also 90 minus theta. So when this is 90 minus theta, and if I draw a vertical line here, and if this is again 90 degree, so this is 90, this is 90 minus theta, then this angle here will be theta. This angle will be theta. So now when this angle is theta, we can easily resolve. Clear? Either you can resolve this into tau WdA into cos of 90 minus theta and into sine of 90 minus theta. Or if you want to simplify, so this will have a component, clear, in this. Let us resolve this with respect to this vertical. So it will have this component here. So this component, this will be how much? Tau into W into dA into cos of theta. Agree? This will be equal to cos of theta. I am now resolving this with respect to this theta here, this one. So this will be cos of theta. And then it will have a component in this direction here. So because this component is opposite to this theta, so that's why this component, this will be equal to tau W wall shear stress into dA. This becomes a force, and this will be equal to sine theta. This will be equal to sine theta. So now I need to simply calculate that what are the components in x direction. So in that case, we can say that because it is a differential element, so dfx, that will be equal to pdA cos of theta. You can see here this component, pdA cos of theta in x direction, clear? And x direction for this force, that is tau WdA into sine theta, this component here. You can see here, this is in x direction, clear? And this is in x direction. So this will give us the differential force, clear? So this is the force which is acting in the x direction on this differential element dA, which is shown here. Similarly, in the y direction, if I want to calculate the force acting in the y direction, so you can see here that dFy will be equal to minus pdA into sine theta. Why? Because this component here, pdA into sine theta, it is in the downward direction. Because it is in the downward direction, so that's why minus pdA into sine theta. And you can see here this tau WdA into cos theta is in the upward direction. So that's why it has a plus sign, tau WdA into cos of theta. So now basically what we want to calculate the drag and the lift force. And how we define them, that the drag force is the component of the force parallel to the free stream. Parallel to the free stream. So now in this case, you can see here, this is parallel to the free stream. But this is actually your drag force. This is how you can calculate for a differential area dA. And then we define the lift force, that it is the component of the force perpendicular to the free stream. So now in this case, you can see here dFy, it is perpendicular in the y direction, perpendicular to the free stream. So this lift force is actually your dFy. So this is the force that we calculate for a differential area dA. Now the net and components of the force on the object, now instead of area dA, if we want to calculate the total drag and lift force on the entire area, so what we can do is that we will integrate. Clear? We integrate this equation. Clear? this equation you integrate, this is for the entire body, we can calculate the drag force. And if we integrate in the y direction, then we will be able to calculate the lift force. We are just integrating the above two expressions in order to arrive at the total drag and lift forces acting on the body. And these two forces, if you want to calculate the resultant force, then you can see here that if we want to calculate just one force, then it can be, this is the resultant force, and we can calculate its orientation, let's say denoted by phi. So if we are interested to calculate their resultant force, then it will be easily calculated provided we know the components. So we can calculate the total resultant force and its orientation. Or conversely, if the resultant force and orientation is given to us, we can calculate the two components of the resultant force. So now we studied that whenever a body is moving through a fluid, or when a fluid moves past a body, so then in that case, two forces are acting. One is known as the drag force, which is parallel to the direction of the motion, and the second one is the lift force, which is normal or perpendicular to the direction of motion. And now we learn how to calculate these two types of forces. So now in this case, you can see that we have to evaluate these integrals. Clear? We have to evaluate these integrals in order to calculate the drag and the lift forces acting on a body. Now in these forces, you can see that they have two components. The drag force, the lift force, they have two components. You can see summation of the two components. So this component, this is due to the pressure force, and this component, that is due to the shear stress. Clear? This is due to the pressure force, this is due to the shear force. So now in order to calculate the drag and lift forces, clear, on bodies, we have to evaluate these integrals. And to evaluate these integrals, you can see here that for each of the differential area, you have to calculate that what is the force acting and what is the shear stress developed and their orientation. So it becomes very difficult. Clear? This is very difficult procedure, that for each of the differential area dA, we evaluate these integrals and then arrive at the total drag force and the total lift force which is acting on a body. So that's why we have a more convenient way of calculating the drag and the lift forces. Clear? This is of course very accurate way that we can arrive and calculate these forces, but calculating these shear stress and the pressure, clear, and their orientation for each of the differential area dA, it is very difficult to calculate. Clear? Or we can say it is not convenient. So that's why in the next slide we would like to learn the alternative way to calculate these forces. Clear?